above this point, all the aerodynamic effects are smaller. This is the worst case. It's right at Mach 3 at 60 kilometers. A milli is very, very good for almost all the research people want to do. Okay, so this is a much better laboratory environment than what you get in the 20 seconds of an aircraft parabola. And aircraft also have a lot of vibrations from engines, turbulence on the body, and wind shear in the atmosphere. I've done a lot of, I've done 50 aircraft parabolic flight experiments. It's a perfectly good place to do research. But you do different research in different formats or different flight formats. And so I'm really excited to get the much lower G levels, the smoother, that is less bouncy, and then 3 minutes instead of 20 seconds from aircraft. So I'm really looking forward to this type of work in the rocket. All right. So here's a sketch of what they think their new vehicle is going to look like inside. The vehicle I showed you was their prototype. They call it the Virgin Spaceship Unity, or VSS Unity. And that flight in June of 24 was its final mission. And now they're building 2 new vehicles, what they call their Delta class vehicles. And these are intended to be operational vehicles. Unity was always only a prototype, and they've learned a lot doing it. And so the Delta class will look like this. You may say it looks like 12 seats. Coming from the left, 1, 2, 3, 4, 5, 6, 6 more on the right. But the back wall of the cabin is a mirror to make it feel bigger. Maybe that's a common trick in small dining rooms and apartments too. So there's actually only 6 seats, not 12. And so one of those seats will be pulled out, probably one of the back ones, and an experiment rack will be put in. This cabin is a minivan going to space. Okay, it's not big. Here is from our automated experiment earlier. This is a good view of the gold and white box on top here on the left, and now the mirror behind it is obvious. The lower box from University of California, and both of these were automated experiments. And here's my in the lower right. Those are my 4 seniors. That's right when we handed it off to Virgin Galactic the day before the flight. We did everything we could to have it ready, and then we handed it off, and they installed it in the vehicle and hooked up electrical power. And that's upper right. Just a couple of their engineers. That's actually the experiment coming off the vehicle. On the left, you see this gentleman stooping over. That's the hatch. You see a kind of a dark region. You know, that's the hatch that you climb in and climb out of, and the experiments go in and out of. So what's Purdue 1? So our team here, me, flying the experiment we call SLICE, the Spaceflight Liquid Interactive Control Experiment. And then Abby Mitzi, my graduate student, that's in the photograph, that's me on the right. This was at the announcement we had in September. Me on the right, we're all wearing Virgin Galactic hats. Abby is right next to me. She'll be flying her human rotational slosh experiment, and this is for her master's thesis research. So, yeah, we're leading the way where graduate research and soon undergraduate experiments can be done in space by the student. I think that's really, really cool. Okay, when I was in your seats as an undergraduate, the space shuttle was starting to fly. And that was just amazing. And now, all these years later, yeah, the space shuttle flew 135 missions, and we're done with it. And now students are going to go do their own research in space. I just think that's so cool. In the middle here, Jason Williamson. He's a Purdue engineering alumnus. He graduated from civil engineering many years ago, runs a large civil engineering company in Texas. He bought a seat to fly with us. And there will be two other alums to be named soon by the Dean of Engineering, who is the guy on the left in this picture. There's a lot of alums that want to fly with us. That's really cool. That is $600,000 for that seat. Sounds like a lot, but cheaper than Blue Origin. And there are 2 automated experiments that will also be added in because the payload rack holds 4 experiments. So there's mine and Abby's, and that leaves room for 2 automated experiments, and those will be named soon. We've had a lot of Purdue people interested in contributing that, and so that'll be announced soon too. And then the question is, well, where do you get all this money? I mean, Purdue must be really rich, right? Well, me, back in 4 years ago, I wrote a research proposal to NASA, and they said it was good enough, and they picked it and are providing, NASA is providing the money for my seat and my experiment. Okay, not Purdue. NASA sees this suborbital research as a new field that they think can be very productive for them for advancing spacecraft technology, proving different things, different sensors, different devices work in weightlessness. People can operate them properly in weightlessness, astronaut training, all kinds of things. So NASA is interested in getting into this. Abby, our college is raising money for her to pay for her flight, and already different people have started putting in a lot of money. It's really nice. The 3 alums are buying their own seats. That's money. And the researchers with the automated payloads are paying for those. Those are each $150,000 each for the flight. So there is no tuition money from students going to space flight. No tax dollars from our state government is going to space flight. We're doing this all on outside money, and so this is all, we're able to do this in addition to Purdue's primary education and research mission. So we're not taking anything from students here, all right? What are our experiments about? Well, Jeremy can certainly explain. When a liquid and gas share a container or tubing in weightlessness, wicking, capillary action rather than gravity, controls where the liquid sits and how it moves. And this is so different than what we are accustomed to here on Earth. We've grown up every day working with liquids, like in a coffee cup with gravity always being present. This is what we know about, okay? So I do have a small movie here. I realize I hadn't brought it into this, into my folder. I'm going to stop sharing, and you'll have to just pardon me for just a minute while I get the video ready. I know right where it is. I will show you. It's something we did long ago with draining of propellant tanks in space. Okay, here we go. So let me get back to sharing. Here we go. All right, you see 2 green blobs? Yes? Hopefully. All right, so this was a rather old video. That's why it's low def. We're trying to repeat this next year with high def modern cameras. This was from 1999. But the green is the liquid, and each one of these tanks is a scale model of what was in the Cassini spacecraft that explored Saturn. This was the main fuel tank in that vehicle. On the left, you see that shape in transparent plastic and green liquid. But on the right, there's something else in the tank, and you'll see that these are what we call propellant management vanes. They're sheet metal. And this video we made to show the operation of how these things work in zero gravity. We didn't invent these vanes. It's at this point, it's about a 60-year-old invention from early in the space age. And so I'm going to roll the video, and what's going to happen is this is in parabolic aircraft flight. And the first thing you'll see is that the flat surface we have on the liquid now, like in your coffee cup, is going to become curved. And that is when we enter weightlessness or zero gravity. When that happens, then we start pumping liquid off the bottom of the tank. Well, we start pumping volume. Whatever is at the bottom, the outlet at the bottom of the tank is going to get pulled out by a pump. And you can see the difference in the two performances. And then when the parabola is over, you'll see the liquid surface go flat again when we get to the double gravity after the parabola. So let's watch this. We can watch it a couple of times. Here we go. So again, the liquid surface starts becoming curved. That says we're entering weightlessness. Now we start pumping. Out the bottom, you see on the left, oh, the liquid went to the wrong place, so we're pumping air out. Now we're pumping liquid, now we're pumping air. Whereas on the right-hand side, it's always liquid at the bottom of the tank. And then when we finish the parabola, here you see in the liquid surface flattens out. You see on the left that there's a lot of liquid left in the tank, and on the right, it's almost empty. And so that shows you how much air has been pumped out of the left-hand tank, which is not what's wanted. Once again, you want all liquid out because that liquid goes to your thrusters for like station keeping or maneuvering in your vehicle, and you don't want to have your pressure and gas running through there. You don't get any thrust, and it just messes up performance and sometimes lifetime of your thruster. So this is, if you grew up with zero gravity, you would think this was normal fluid behavior, okay? Okay, let's go back to the PowerPoint. Not that. Okay, so splice, my experiment, you'll notice that water wets plastic surfaces unevenly, what we call pore wetting. And there are many uses for this in space flight, life support systems, plant growth, medical. And in zero gravity, this pore wetting phenomenon is even more dominant for controlling the liquid. And it's highly nonlinear. It's difficult to model. And that's why we were able to get funding to go do experiments on it, because you can't sit here at your desk and model it with computational fluid dynamics. Well, big enough computer, enough money, you can get a good start on it, but it's still a really tough thing. So we're going to get some really useful data for that and some second and third impact from that too. Rotational slosh experiment studies what happens. Let's say you're in a spacecraft and you rotate to dock with a space station. When you rotate, that put liquid propellants into motion, okay? If you have a bowl of soup and you turn, you put the soup in motion, and as you stop, it wants to slosh out of the bowl. Well, the liquid propellant is very much the same. Here on Earth, that soup is pulled back into the bottom of the bowl by gravity, but that's absent in this space flight. And so it really is capillary effects, surface tension, and wetting that want to pull the liquid back. And those are much weaker forces on the liquid than gravity is. And so this becomes an issue for space flight control, maneuvering, pointing capabilities, in-space refueling, and more. And so these are what our two experiments are looking at. Here's an example. I told you rotational slosh fluid is an automated experiment. This is what it looks like inside that gold box. Each one of those transparent acrylic tanks, this picture is wrapped in blue tape to try to protect the surface from scratches. But notice, if you will, on the lower right, you can see a camera lens, little camera lens. I don't know if you can see my cursor, but that camera lens basically looks up to a mirror and over to the four tanks on the far side. And on the left, you see the backs of two actually modified GoPro cameras. And those are looking down into mirrors which look at the tanks on the right. So there's four cameras and 8 tanks in this experiment. By the cameras in the back left, you can see a gear on top of a motor and a rack, and that's what's creating the rotation of the tanks during the space flight. This worked really nice. Here's four of these tanks. Again, actually the same tank that was in that old video. Why? Well, it's typical of interplanetary spacecraft tank design, and it was published in the 1990s, so I don't have to worry about export control. It's a public design. It's out in the public already. I don't have to worry about secrecy or anything. So we had on the left 20% full, 60% full, moving to the right, 40% full, and 80% full. So these four tanks, and the bottle in back says silicon oil. Indeed, this is a very good wetting liquid, like the traditional propellants. We had four other tanks with a poor wetting liquid, like some of the new non-toxic propellants. And so we had quite a bit of things in there. On the left, that's in vibration testing. There on the left, standing up, that's in our mechanical engineering school here at Purdue. They have that a shaker table large enough for doing a 50-pound experiment. You know, it's very interesting. I've told you these are girth vehicles, right? They keep the G loads low, and they flow 90-year-old people. Well, if you look at the Blue Origin vibration test spectrum that they want, under 400 hertz, the rocket flight is gentler, smoother than what Federal Express shipping company says you should tolerate for their shipping. So this is very gentle space flight. It's not going to orbit. Right? If you go to orbit, you need to go 3 to 4 times higher, and then 27,000 kilometers per hour sideways. So that's a lot more energy than we're talking about in these rockets. On the right, then, is a picture of it at the Spaceport of America. You see the red liquid, and then the 4 tanks in front of us. They're at the bottom here have the green liquid. They're in plastic bags because flight companies want liquids in levels of containment for safety. The first level is the test vessel, and the second level then is this plastic bag. And so again, you can see the gear and the rack in the bottom here that's creating the motion there. Our electronics, and so this is all student designed, students like you. It was several teams over the course of about 3 years designing, and this they don't do the machining of the parts. We have a machine for that, but they design the parts and work with the machinist about what should be done. That's me putting one in a plastic bag. And this is out. You can see you can see the Virgin logo on the tail. The mothership was parked right behind us. It was a fun week working in the hangar there, right alongside the spacecraft. And that's the Berkeley team behind me, and Virgin Galactic's ubiquitous photographer. Never seen people take so many pictures. There we are again in the vehicle, and you see this Berkeley below and us above, 2 different boxes. And this on the left, there's a vertical kind of a light gold colored frame. That's the payload rack I keep talking about. That attaches to the vehicle where a seat would. And so these are the bottom 2 spots, and you see the 2 spots up above in front of that window. We also learned that they need a sunscreen on that window. It heated up, the sun heated up one end of our experiment, and the cameras on that end overheated and shut down. So that was unfortunate. But we learned. So, and again, that's removing it from the vehicle. So to summarize, so we have a Q&A time. Maybe I've run a little long. Purdue 1, it's an all Purdue flight, 2 human-tended experiments, 2 automated experiments, 3 space tourists. Possibly they will have pocket experiments or wearable medical sensors. That's coming down the road still. This is the first time a grad student will do their research in space. The first 2 major human-tended research experiments in commercial suborbital space. It's the first university charter flight. You need to have a your professor there start lining up money for for your flight. And this whole process, I really like that we involve undergraduate students like you in experiment design, fabrication, ground testing, and a subset of them get to go out to the launch site and do the actual launch support and final experiment preparation. So we're blazing the trail for other universities to follow Purdue. And Virgin Galactic says we'll fly in 2027. So you say, well, that's 2 years from now. That's a long time. But I remember watching the Apollo 11 landing in 1969 when I was 8 years old. So I've been waiting a long time already. And a year or two doesn't really bother me. We're going to get there. It's going to be so cool. And that's what I stopped sharing. And I'm sorry I didn't leave much time for questions. How do I make it? How do we make it more accessible for other people? Is that the point? Okay, very good. That's a good question. Because I tease the students in my class that they shouldn't sit there thinking they missed out on Purdue 1. They should sit there thinking about how will they create Purdue 2. So yes, the cost needs to come down, right? For that box to fly by itself is $150,000. And then if you want to fly with it, it's $600,000. So that's expensive. But I see costs coming down. The new vehicles that Virgin Galactic is bringing out should be able to fly every third day. Blue Origin wants to go to almost a weekly cadence with multiple vehicles. So there's going to be more and more opportunities provided by the rocket companies. And once they've gone through the excited millionaires, they're going to find nobody else wants to spend that much money. So I think the cost will come down, just like when my parents were your age, airplane travel across the United States so expensive, only movie stars type of people did it. And 40 years later, they would pick up the phone and buy a ticket to fly the next day all the way across the United States just to see their grandchildren. So air travel, the cost of air travel has come down a whole lot in a fraction of a lifetime. So I would say one thing to do is, anticipate the future that the cost will be more accessible. Another approach might be, well, what if you were to put 4 experiments in that box? Then there's more people involved. There's more opportunities, and maybe that means 4 different sources of funding can come together and collaborate for one. So I think that's a creative way to look at it. Also, the parabolic aircraft flight is cheaper. For one person with a small handheld experiment is about $10,000. So that's much cheaper. And right, you're not going to space, but it's still a research opportunity. So that's a cheaper way there. Here at Purdue, we have a 2-second drop tower for short duration, low gravity, not for people, for experiments. That's another research option. Hello. Okay. Guillermo, could you repeat that carefully? That was the audio is not good. Very good. Um, you don't know the future. Um, you look at me and say, you know, I, I think I'm doing cool things, and maybe hopefully they're attractive. But I've done a lot of other things on the way here. I see a Cummins sweatshirt, a jacket right in the front row. Somebody has a Cummins logo. The young lady on your jacket. I did work for Cummins on diesel fuel injectors. I did hypersonic optical diagnostics. I did oil flows and Rolls-Royce turbine engines. You just have to, whatever the money is, you do the work. For preparation for you guys, you're right now we're in this AI revolution, right? And it's going to be interesting to see how that shakes out because it's overhyped. There's some good there, there's some power there, but it's really not intelligent. It's really just averaging all the information it's been trained on. So you have to be smart about how to use it. And another revolution going on is quantum computing. Um, I'm old enough where I can say, "Oh, that's not going to help me. I don't have to learn that." But people your age, you ought to be aware of what capabilities that brings. That's going to be another. Both AI and quantum computing are tools in your toolbox. Um, Alone, they're not going to change the world, but with people like you using them in smart ways, great things can happen. So that's kind of a broad answer, not too detailed. Yes, all the traditional physics, chemistry, math, that is your engineering background, are tools you're going to apply with these new powerful tools and make cool things happen. Um, I am terrible at predicting the future. Um, I won a National Science Foundation award as a young professor, but my proposal for that included a statement that this whole internet, World Wide Web internet thing will never catch on. It's going to amount to nothing. So obviously I'm wrong. I'm talking to you here from thousands of miles away by video. So yeah, just work hard. Um, Students want career advice. Say work hard and don't fight dumb luck. If good things are happening to you and you're trying to choose otherwise, maybe you should just let good things happen. Um, so yeah. Okay. Um, I, there's an echo. So, Guillermo, could you help me out again, please? Yeah, I don't know. My younger years, I did work on some military systems. One of them is hanging in a museum in Washington D.C. now, which makes me feel really old. Um, but no, I had no problem trying to keep my family safe. Um, and so yeah, I never saw any ethical issue at all with that. Nor with working on, nor with like all the millionaires flying on these spacecraft. Um, Things like flat screen monitors started out as luxury items, and now we all have them in our pockets, right? So that's the natural economic progression of of the market, of the free market. So yeah, whether it's luxury space flight or whether it's military systems, I haven't had any problem um, doing that. Has I ever had any? Let's see. Um, yeah, I don't know. I can't think of the ethical issues I've run into more are on how people want to misspend money here on Earth on all kinds of things, and that sort. Or yeah. Hmm. Yeah, certainly. My experiment is funded by NASA, and the data is supposed to go into something called the physical science informatics. So it's a database NASA runs of experimental data, typically from space station, but from other vehicles too. So it's supposed to go there to be publicly accessible, um, and then privately funded work is under no obligation, but certainly advancing. I mean, Abby will have a master's thesis. There'll probably be more analysis after that. That I've a previous experiment that flew on Blue Origin. We're finally wrapping up some data analysis, and that'll get out into the AAA journals. And so that's those are the usual ways. It's kind of funny that my end of fluid physics, that is the zero gravity work, is very obscure. Not many people care about it. So it's not like healthcare where everybody's interested. Yeah. Morning. Yeah. Yeah, that's a very good question. Um, really, so I started working in this suborbital field in 2009, and a lot of us space nerds would say, "What experiment would we have? Could we propose that we have to be there with?" And the answer comes down to be something that is sufficiently nonlinear that is very difficult to predict. Because if you need to automate it and it's really tough to predict, you're adding in more and more compute power, more and more controls, more and more diagnostics, and pretty soon you don't have enough electrical power to do what you want, or it gets too big, or it's putting out too much heat in the cabin, and it just becomes simpler to put a person there. Um, and so that's um, how we came down to this: is that the liquid motion is sufficiently nonlinear that we CFD cannot compute it well, and so now we're using CFD to try to help us, design successful experiments. But for example, on my liquid capillary advance payload, there's going to be parallel plates that I can control the spacing and the tilt, and that creates a wicking channel. And just like if you put water on a tabletop there, it won't form a perfect circle. It wets more in some directions than others. That's the imperfect wetting that we're dealing with. It depends on the liquid, the solid material, the surface of the solid, the cleanliness, when was it last wetted, what particulates are in the air, all kinds of things, temperature gradient. So it depends on a lot of parameters, and that's the other way is that makes it hard to automate. Is the phenomenon depends on so many parameters that it's easier to put a person up there to make decisions than to try to automate, build in the sensing and the decision and the actuation needed to automate the experiment. Now there are a lot of things I think one could do from uninhabited spacecraft in orbit if you had good stereoscopic video telemetry. If you could see stereoscopic video of your experiment in orbit and sitting at your desk on your web browser, then you could adjust things in the experiment. You could do a lot of good work that way. But yeah, you don't actually need the people in space station. So yeah, that's how we got here. Okay. How difficult is doing what? How difficult is what? Ah, well, yeah, that's it can be difficult. If you think about a tank and putting liquid in one end of it, if you pump slowly, it fills, it wets the surface and fills up. If you pump too quickly, it shoots all the way across the geyser. And we've actually had them on parabolic flights. We've had liquid go from the inlet right to the outlet without ever staying in the tank. So for my experiment, all right, for rotational slosh, those are filled on the ground. There is no liquid transfer. That turned out to be a way to get more data than having pumps and reservoirs in the experiment and trying to move liquid around. By taking out pumps, taking out plumbing, taking out reservoir, we had room for more tanks. And so there is no liquid transfer in rotational slosh. In my experiment, yeah, it's tricky for a couple of reasons. It's difficult to anticipate where the liquid wants to be because we don't have intuition about zero gravity fluids positioning. There is a computer code called Surface Evolver. I think Guillermo learned it, which allows us to do a lot of unique work on the statics of capillary liquid positioning. And I'm using that to try to design this experiment. For my experiment, liquid, when we take off from the ground, the liquid will be in a bladder, right, a bag. And then during rocket boost, it will be pumped into the experiment chamber because the boost is 3 or 4 times gravity, and that will keep the liquid very much where we want it to be. And it will also prevent the foam from forming. It's easy in zero G also to, if there's any pulsation in the liquid flow rate, you can grow a foam in your experiment, which of course would allow you to do no data. But with the high G, you can't form a foam. So we're doing it that way. If you need to fill something in zero G reliably, either do it really slowly, or figure out a way to keep liquid in contact with the surface well. And there's a lot of things that have been tried, and then test it in the airplane. Make sure your idea where you think the liquid is going to go is where it's going to go. I did design a space station experiment for a good friend and colleague named Mark Weisslogel back in the 2004, 2005. And when it first operated in space station in 2006, we were absolutely shocked at where the liquid decided it wanted to go. And we were supposed to be 2 experts. So actually, that was a human error in the design. But it's a longer story. But fortunately, it did not prevent the experiment from working, and actually taught us more things. But yeah, you got to test. NASA Technical Report Server is a public database of a lot of NASA work since a century ago. AAA journals are another big place for trying to figure out what's been done, see what people are doing. So yeah, you got to go look and see. Mm-hmm. Are you asking about getting hydrogen from the atmosphere? Right. Yeah, I don't think there's enough up there. Um, um, yeah. I mean, hydrogen from lunar and Martian soil, there's more there. A lot more molecules per cubic centimeter in a solid than in the upper atmosphere. Yeah, I don't know. You'd have to have a pretty big scoop to try to scoop up enough air and throw out almost all of it. Try to save the hydrogen. Yeah. Mhm. Mhm. Right. So a three-phase flow problem. Solid liquid gas. I haven't done much with that. Um, I've I did some work many years ago on a liquid wicking problem in space that had little pieces of hair and skin cells on it. It was for a, a rodent habitat in space station. So for lab rats, and lab rats are messy animals. Um, yeah, it's I've never done anything like that. But if we're going to indeed create fuel from lunar resources, it's going to be extremely hard to keep the dust out. And so systems that tolerate the dust are going to be needed, I think. It's interesting. The lunar I've had the pleasure. I've met three of the 12 lunar astronauts, and in one sense, they all talk about the dust. The dust was everywhere, and the dust was a nuisance. And the dust is actually very sharp particles because there's no erosion to wear them down like here on Earth. On the other hand, almost all of those lunar astronauts lived to be pretty old, so it couldn't have been too bad. Um, yeah, actually, Jack Schmidt, the geologist on Apollo 17, I introduced at a conference 3 years ago, and he was 90 years old then and still doing research. That was pretty cool. But yeah, the three-phase flow problems come up here on Earth and also in space flight. And I've never messed with them. If you want job security, pick a really hard problem like that. Oh, well, that's a fun question. I hadn't thought much about that as I'm a user of the rocket, not the designer of the rocket. I joke that I need to lose some weight so that every kilogram I lose maybe is another 50 milliseconds in space for me. Um, but yeah, I mean that's the rocket equation. Um, yeah, it takes fuel. You have to burn fuel to lift fuel. So it's and actually that's where the airplane going up to 13 kilometers is a good start. Um, yeah, I don't know. That's an interesting question. I also find it interesting that Virgin Galactic drops a rocket that zooms up. Um, Blue Origin has a traditional booster and capsule designed to do the very same mission. And there was a third company, XCore. Unfortunately, they went out of business. They had an even different solution. They had a space plane that would take off from the runway and zoom up all on its own. So there were three different solutions to the same problem, and it was interesting. I actually had a somebody writing for television shows contact me, and they said they were trying to put a show together about space race, and they wanted to have a company with some rocket idea, and they just wanted to know, was that a crazy idea? And I say, no, that's not a crazy idea. There's already three ideas out there. There's no standard solution here that exists that everybody says, oh, yes, okay, the light bulb has to screw in this way. And so it was wide open. So yeah, it's a lot of different ideas. Okay. Good morning. Right. So the question was during my last mission, did did we behave? Right. So unexpected behavior that we saw. Um, in zero G, it did not slosh as much as we expected, but we have to go back to the scaling laws. I think it was too viscous of a liquid. But the big unexpected thing really was the transition to zero G. I've flown 11 experiments on Blue Origin, which is a rocket that goes up. Um, and so the bottom of the experiment on the ground is the bottom of the experiment during boost. For a Virgin Galactic, the bottom of the experiment on the ground is not the bottom during boost, because during boost it's accelerating like towards the nose, and so the fact that the liquid would reorient during boost from the ground condition to boost condition and then to zero G, I felt really stupid. I had not anticipated, and so we're doing a better job of handling that in Abby's experiment. What that did was that wasted time for us. The liquid eventually got to its zero G position, but we wasted 20 or 25 seconds of the experiment time having to wait for that to happen. Yeah, what specialties are most valuable? I would, if you're thinking about a career as opposed to the field in general, if you're thinking about you, any person, I would say one of the things that um, was important for me was to be able to do work in 1G that paid, while to get through the downturns in space. And so it's if you want to work in capillary dominated fluid physics and space flight, well, on Earth there's micro devices, including a lot of miniaturized medical devices, and so be familiar with that field. So have both a space and an earthbound application for your knowledge is something that can help you persist in the space field. Then within spaceflight itself, and you mentioned astronauts, I mean, we are only now starting to really get into the fluid physics of how to grow plants in space effectively, large amount of plants in space for Mars missions. Human physiology and zero gravity is still a very young field. So the more you can the more you can bring in biological knowledge into your fluid physics knowledge, the more marketable your skills will be, the more unique problems you can attack. I would say also, people have asked me, what experiment do you want to do on the lunar surface? And my answer is, well, I don't have one. My area of fluids, the moon is just, it's going to be a little bigger coffee cup or a little smaller. It's not going to be a lot of different. But when you have more physical processes involved, if you're doing combustion, diffusion, chemical reactions, competing chemical reactions, biological systems, separations of solids and liquids and whatnot, the more complex the physics, the more important or the more challenging it is to do on Moon and Mars surface, not just in space. So I would say, the more multi-physics your expertise can be, the more marketable you're going to be. Perhaps I wandered off a bit there, but hopefully that's helpful. And Guillermo, I'm going to need to go now. Very good. Yeah. And so now you have a program also. You have a program now with Embry-Riddle, right? Do your students go there for grad school, or is it remote? Very good. Oh, good. Well, their dean of engineering is a Purdue graduate, Purdue aerospace graduate. I remember him when he was a PhD student out at the wind tunnel labs. So, yeah. All right. Great to see everybody. Good luck with your studies and on finding a way to space, be it for your experiment or for you. And Guillermo, if you need if you need a contracting, a purchasing agent at Virgin Galactic, let me know. I'll give you their name. All right. Bye bye.